Data mining is the automated computer science process of extracting valid, novel, and useful patterns from massive, complex datasets. To find these hidden structures, data scientists rely on standard machine learning models, like descriptive clustering algorithms, which group unlabeled data based on mathematical distance. But as datasets grow from thousands of rows to billions, and as each record gains hundreds of distinct attributes, the distance calculations multiply exponentially. This is the curse of dimensionality. Upgrading a single server's CPU and RAM, a strategy known as vertical scaling, eventually hits a physical limit. A single machine simply cannot hold or process petabytes of high-dimensional data in memory. Traditional database processing and single-server machine learning break down at this petabyte scale. Continuing the analysis requires a different computational architecture. As shown, instead of forcing one machine to handle the entire load, the solution is horizontal scaling, distributing the dataset across a peer-to-peer cluster of commodity servers. Distributed machine learning operates by sharding the massive dataset into smaller, manageable blocks across this entire network. To coordinate complex machine learning models across these separate physical machines, engineers use specialized frameworks like Apache Mahout. Mahout relies on an underlying computational substrate called MapReduce to execute these algorithms in parallel. Operating machine learning at this scale involves translating established algorithms into the physical constraints of the MapReduce architecture. Consider the k-means algorithm, a descriptive model designed to group unlabeled data points by mathematical proximity. The translation begins with the splitting phase. A central master node takes the massive input file and slices it into discrete, equal subdatasets. These chunks are then distributed outward, assigned to a wide array of horizontal worker nodes. This triggers the map function. Each individual worker node processes its specific subdataset entirely locally, transforming the raw data into a structured collection of key-value pairs. In the context of k-means, this means each local worker calculates the distance of its assigned data points and maps them to the nearest local cluster centroid. By breaking a global calculation into isolated tasks, the map phase processes millions of records simultaneously, without requiring any shared memory between nodes. At this stage, thousands of isolated worker nodes hold disconnected local results. To build a cohesive model, these fragments must be centralized. This is where the shuffle and sort phase takes over, acting as the database's automated network routing layer. The network intercepts worker node outputs across the cluster, identifying pairs sharing the exact same key. These identical keys are grouped, placing all matching values into a single array, then automatically routed along network paths to pre-assigned reducer nodes. The shuffle and sort phase organizes thousands of disjointed local computations into the structured inputs required to finish the algorithmic calculation. Finally, the system executes the reduce function. The assigned reducer node ingests the grouped array and performs an aggregation, such as a sum, average, or count, condensing it into a single final value. For k-means, this computes the new global cluster center from aggregated local distances. Because data is distributed across dozens of commodity servers, hardware failures are inevitable. MapReduce provides fault tolerance, ensuring no single point of failure. If a worker crashes mid-calculation, the master node executes a contingency protocol, instantly reassigning that specific map task to a healthy node in the cluster. This design ensures that an algorithm reaches completion despite physical hardware failures. To understand how this fits into an enterprise architecture, this linear block diagram illustrates the knowledge discovery in databases, or KDD, process. KDD is a 7-step iterative framework designed to turn raw, unstructured data into actionable business knowledge. The sophisticated algorithms executing on our MapReduce cluster and managed by Mahout sit exactly here at Step 5, data mining. But the success of Step 5 depends entirely on the prerequisite stages, data cleaning and data integration. Unfiltered enterprise data is frequently noisy, incomplete, and filled with inconsistent naming conventions. Processing uncleaned records leads to inaccurate models, a vulnerability known as garbage in, garbage out. The most powerful distributed machine learning architecture in the world is functionally useless if the preceding extraction steps feed it corrupted data. Distributed machine learning does not alter the underlying mathematics of predictive and descriptive models. It executes them on an entirely new scale. Frameworks like Apache Mahout deploy these standard algorithms across horizontally scaled, fault-tolerant clusters, ensuring continuous uptime and linear performance gains. The computer science industry has abandoned the reliance on a single, massive host machine in favor of swarm computing. Modern machine learning scales through the coordinated execution of thousands of independent nodes working in parallel.